So welcome to this video on methods in differential equations. We're looking at first order differential equations. You've already met first order differential equations in the single maths syllabus, and we've seen how we can solve first order differential equations by separating the variables. So we rearrange our equation so that we have everything with dx in on one side of the equation and everything with y and dy in on the other side of the equation, and then we integrate both sides. However, we're now going to meet some equations where we can't do this. So if we look at the first example here, x squared dy by dx plus 2xy equals cos x, it is not possible to separate out the x and dx and the y and dy there. So we have to use a different technique. And what we're going to do here is we're going to use some more of the differentiation that we know. So using the fact that integration is the reverse of differentiation, we're going to notice that if we differentiate x squared y with respect to x, so in other words, we're going to find d by dx of x squared y. Well, we're going to do that using the product rule and using implicit differentiation. So we say we differentiate the x squared, that's 2x times keep the y the same, plus x squared times differentiate the y, which is just dy by dx. Now I've got this the opposite way round, but it is equal to the left-hand side there. So what we can do is we can say, reversing that process, if we integrate 2xy plus x squared dy by dx, we're going to get x squared y, and then we've got to integrate the right-hand side. So let's go ahead and do that. I'm going to write it on the pages here. So we've got x squared y equals integral of cos x. So that's x squared y is equal to sine x plus a constant of integration. And then usually we'd like to rearrange that into y equals, so that's going to be y equals sine x plus c over x squared, or we could write it as x to the minus 2 sine x plus c x to the minus 2. So that is using the product rule in reverse to solve a differential equation. Now we're going to generalize that that technique. So if we look at the second example here, it says find the general solution to this differential equation. dy by dx minus y tan x is equal to 3 sine squared x. Now, it's not always quite as simple as looking at the left-hand side and saying where did that come from. So there is a general way to do this. What we're going to do is, if we don't have our equation in this form, dy by dx minus some function of y, y times some function of x is equal to a function of x, then we're going to rearrange it to that as our first step. We'll see that in question 3. Question 2 here, we do have just dy by dx here, so we've got this in the form that we want. What we do now is we need to multiply through by something called an integrating factor. So the integrating factor, let's write this down, factor or IF, is equal to, well, we want to take what the y is multiplied by here, so that's minus tan x, and we're going to find e to the integral of that. So we want e to the integral of minus tan x dx. When we integrate minus tan x, we get minus ln of sec x. So it's e to the minus ln of sec x. And that's e to the ln of sec x to the minus 1. So that's sec x to the minus 1. Sec x to the minus 1, which is equal to cos x. Now, what do we do with that integrating factor? Well, we multiply through both sides of our equation by the integrating factor. So we're going to get cos y times dy by dx minus y tan x cos x is equal to 3 sine squared x cos x. And then we're just going to perform a simplifying step here. So tan x is sine x over cos x. So tan x times cos x is just sine x. So we've got cos y dy by dx minus y sine x is equal to, I'm not sure, is equal to 3 sine squared x cos x. Now we can integrate both sides. That left-hand side just comes from using the product rule. Hopefully you can see where it comes from. It's going to be cos y to, sorry, this should have been cos x here. There we are, cos x. Excuse my mistake there. I have multiplied by cos x there, and I just wrote y where I should have written x. So it's going to come from cos x times y, because when we differentiate cos x, we get that minus sine x. So this is y times cos x on the left-hand side, and then we're going to integrate the right-hand side. If we integrate the right-hand side, well, that also comes from effectively, well, from using the chain rule. Using the chain rule in reverse, we're going to get sine cubed x plus constant of integration. Okay, if you check sine cubed x, differentiate it using the chain rule, we get 3 times sine squared x times derivative of sine x, which is cos x. So we've got y cos x equals sine cubed x plus c, and now we can rearrange that to finish up with y equals sine squared x over sine cubed x, I'm sorry, over cos x plus c over cos x, or something equivalent to that. We could write this first term as sine squared x times tan x. We could write this as c times sec x. So both of these examples we've seen so far, we've found a general solution. We would then need initial conditions to work out what that value of c was. Let's go on to the next page, and we have a third example. The difference here is that our differential equation is not in the form that we need it to be in the first place. So for part A, where we're finding the general solution, our first step is going to be to rearrange so that this first term is just dy by dx. So in this case, we need to divide through by cos x. So we're going to say dy by dx plus 2y sin x over cos x is tan x. Tan x is equal to, divide through on the right hand side, we just get cos cubed x. Now we're going to take the whole of the function of x that multiplies y here, so that includes that too, so it's 2 tan x. Our integrating factor, if, is equal to e to the integral of this bit without the y, so 2 tan x dx. When we integrate tan x, we get ln of sec x, so we've now got e to the ln 2 ln sec x. That's e to the ln sec x to the power of 2. E to the ln sec x is just sec x, so we've got sec squared x. So we're now going to multiply through every term in here by sec squared x. So that's going to give us sec squared x dy by dx plus 2y tan x sec squared x is equal to cos cubed x sec squared x, and we're going to simplify to sec squared x dy by dx plus, I'm going to leave this as 2y tan x sec squared x, even though tan x is sin x over, oh yeah, actually that won't simplify anyway, will it? Is equal to cos cubed x times sec squared x is just cos x. Now we're in a position to integrate, because when we differentiate sec squared x, we get 2 times sec x times the derivative of sec x is sec x tan x. So this is y times sec squared x is equal to, integrate cos x, we get sin x plus c. Let's just go over that quickly again. If we differentiate this using the product rule, we're going to get, if we leave sec squared x alone there, differentiate the y, so this times dy by dx, plus leave the y alone there, differentiate sec squared x, we get 2 times sec x tan x times, 2 times sec x times the derivative of sec x, which is sec x tan x. So we get tan x sec squared x. So then let's just have one last step. Y is equal to, if we divide through by sec squared x, that's the same as multiplying through by cos x. So we get cos squared x. So we get cos squared x sin x plus c. So there's our general solution to that differential equation. So for part B now, we're going to find the particular solution if y equals 2 when x equals 0. I'm just going to move that up a bit. B. So at 0, 2, we get this. 2 is equal to cos squared of 0 times sine of 0 plus c. That's cos of 0 is 1, so it's 1 squared times 0 plus c. So c equals 2. And we have the particular solution, y is equal to cos squared x times sine x plus 2. So that's an introduction to how we use integrating factors to integrate first order differential equations. It is very important that you remember some of the terminology for dealing with differential equations. So integrating factors are very important, and we'll come back to them. So the next thing to do is to go away and do some practice of finding and using those integrating factors. So that is in our textbook, exercise 7A on page 151. Okay, I hope that was useful. The next thing we'll go on to is second order differential equations. So that's where we've got a second derivative as well as a first derivative. I'm going to end the video here for now.